We are less than 2 days away from our next opportunity to launch the Space Launch System rocket and Orion spacecraft on a flight test beyond the moon. Welcome to NASA's status briefing for Artemis 1. I'm Rachel Kraft with NASA's Office of Communications. The mission management team met earlier today to review the status of preparations for the mission. Launch of the uncrewed Artemis 1 flight test is currently targeted for Saturday, September 3rd at 2:17 p.m. with a 2-hour launch window. Joining us here at Kennedy Space Center in Florida, we have several guests who will give us an update on the preparations and overall status. We have Mike Sarafin, Artemis 1 Mission Manager, John Honeycutt, SLS Program Manager, John Blevins, SLS Chief Engineer, Charlie Blackwell-Thompson, Artemis Launch Director, and Melody Lovin, Weather Officer with the Space Launch Delta 45th. We'll start with a few comments from our guests, and then we'll take questions. For those of you joining on the phone, you can press *1 to be entered into the question queue. And I will also note we do want to keep our briefing to an hour today to give our guests some much-needed rest. So with that, Mike, let's start with you.
Okay. Well, good afternoon, and thank you for continuing to follow the Artemis 1 mission. If you recall, 2 days ago we had a scrub following the August 29th launch attempt, and we needed a little bit of time to assess our risk posture headed into a subsequent launch attempt, and we reviewed that today as a mission management team. A little bit of time helped us work through all of the information that we gathered from the first launch attempt. And we worked through a number of issues, and we discussed our risk acceptance rationale for a subsequent launch attempt. If you recall from our prior attempt, we had the tail service mast umbilical leak. We had a hydrogen leak in the tail service mast umbilical. That coming out of the last launch attempt, we met and agreed to do some work out at the launch pad. That work has been completed. We had an issue with the core stage intertank vent valve. That has checked out, and we do not consider that to be an issue. We also had an issue confirming that we were able to thermally condition all of the core stage engines within the required temperature limits as part of what we call the engine bleed. And we worked through that today. And then near the end of the launch attempt, we saw some cracks in the foam on the thermal protection system on the core stage at the intertank flange, and we reviewed that issue today. There was some incremental risk acceptance. As the mission management team, it is our role to review risk acceptance and then the flight readiness rationale. And then we also have requirements change authority following the agency flight readiness review, and we review any changes from the previously accepted risk baseline that we had at the agency FRR. And we did that today. Only 2 of those items required some incremental risk acceptance, and that was the thermal conditioning of the engines associated with the engine bleed, and then the core stage thermal protection system, the crack that we saw, specifically what is termed crack number 2 at the intertank flange, just due to the potential for debris transport, and then contact with the booster set motor. It's a low likelihood occurrence, but it is something that we considered an acceptable risk. So we reviewed our risk acceptance rationale and our overall risk posture, and we are setting up for a launch attempt on September the 3rd, Saturday, and we're comfortable with our flight rationale and risk acceptance there. In addition to that, we did have some late analysis come in associated with an off-nominal performance scenario where if we have, and we're not planning on this, but should we have a underspeed at the completion of the translunar injection maneuver, it shows that our trajectory would put us into what we call an eclipse violation, which is a power production issue for the Orion spacecraft. So as a result of that, it is specific to the September 4th launch opportunity. We agreed to take that off the plate. So we are, again, proceeding into our Saturday launch attempt. We're comfortable with our risk posture. That said, there's no guarantee that we're going to get off on Saturday, but we're going to try. And the technical teams have put in a tremendous amount of work in a very short amount of time to get us here. And again, thanks to the work and the effort that they've put in. So with that, I'll pass it back to you, Rachel.
Okay. John Honeycutt.
Yeah, good afternoon. It's a pleasure to be here. I think when I talked day before yesterday, I mentioned that we had a lot of data to go look at. And so, we had come out of the first launch attempt. We were unsuccessful on gathering the data that we wanted to gather for that, what we call the bleed kickstart. The team has done a tremendous amount of work starting right after the launch, even up until this monning and to the noon hour, leading us into the MMT meeting. What I would tell you is they just did an outstanding job nailing it flat, and we'll share some more of those technical details. But at a high level, we have convinced ourselves without a shadow of a doubt that we have good quality liquid hydrogen going through the engines, and there's no fuzz on that. We've also, through the course of analyzing the data, looked at 5 additional measurements that we can look at to assure ourselves that we are getting that quality data. And that's on the engine. That's on the engine side, and then on the core stage side, we were able to go back and verify that the core stage is providing the amount of hydrogen and the quality of hydrogen to all 4 engines. And so I'll turn it. I say Dr. Blevins and his technical team just did an outstanding job working through that, and we'll share some of those details, I'm sure, as we get to the questions.
Okay. John Blevins.
Yeah, I'll just add that we do have an outstanding team, and they did look at the data. We had some things we were looking for in launch attempt 1 that were combined with what we expected to do in a wet dress, and so we had some sensors that didn't tell us what we thought we would do, and we did the right thing by standing down with that uncertainty on Monday. But we have confirmed that we did have good flow through those engines. We know we can chill those engines. We're ready to proceed that way to launch. The SLS team does a lot of other things, and as Mike mentioned, we brought some other things. We inspect the vehicle. We brought the concerns we had over any TPS as minimal as they are forward, and we've analyzed, and the teams are ready to support launch attempts on Saturday.
Okay, thank you. Charlie?
Well, good evening, everyone. It's great to be back here talking to you about our preparations for Launch Countdown. I think we met and talked just a couple days ago, and when we had our last press conference on Tuesday, we had finished up our safing and securing out at the pad, and we were getting ready to send the access stand out so that we could begin work on the LH2 TSMU purge can, where we detected that leak during our tanking operations. That work is all behind us. We finished up the work. We were able to find what we believe is the source of the leak and correct that. And that purge can's been put back together. We have leak tested it at ambient conditions and also done some flow-through tests with our HAZGAS system, and we believe we're in a good configuration for the next loading attempt. We also went back based on what we saw during the, and working with John's team, looking at any countdown enhancements that we might need to make. We have made a couple of changes as we prepare for this next loading operation. And really what that means is that we're going to start our LH2 chill down, the facility side of the chill down, right around the same time that we begin our LOX chill down. So that'll allow us to begin that kickstart bleed a little bit earlier, and we'll pick up that kickstart because I know I'll probably get a question about when that is, and we'll start that just about 8 o'clock on Saturday morning. So we've made a couple of changes to the countdown. Our teams have been very busy in Firing Room 3 running against the model. We finished up 2 days of that testing to make sure that we had our procedures all down and ready to go. It didn't require any software changes. It was just the procedures that we go through, but we also want to make sure that we have those ready to go. And everything right now is on track. We have remained in launch countdown. I know some folks think that, launch countdown, it starts 2 days prior. Sometimes when we're in a scrub, we stay in launch countdown, and that's what we have done this particular time. We've been in originally in a 96-hour scrub. Of course, we added a day on to go do this purge can work. And we've also taken replenishment of both LOX and hydrogen. Both tanks are topped off, which is great. And so we are on track to support our 0557 tanking operations on Saturday morning, setting us up, as Mike said, for that 217 window open.
Great, thank you. And Melody.
All right, good evening, everyone. You got to me a little faster than I thought. Anyway, as I was walking over here, I noticed a lot of anvils kind of streaming in from the west coast, and I even saw some mammatus clouds up there. So let's go ahead and look at satellite and see what's going on. So basically, right now, we actually do have offshore flow, meaning flow out of the west coast, or generally a westerly flow. You can see a lot of thunderstorms popping up across the interior portion of the state at this point in time. They are spreading east, but I actually just looked at radar. You're looking at infrared satellite here. Radar is different. But in general, the showers themselves are staying across the interior portion, not getting close to the Cape at this point in time, but you can see a lot of anvil from a lot of those showers and thunderstorms. But anyway, this pattern that we have today is actually going to be transitioning into more of an onshore flow regime as we get into tomorrow, and that is mainly due to the fact that we'll have a ridge that's building across the state of Florida. And what it will do is deliver easterly flow, and that easterly flow will stay intact for several days. So that's actually normally pretty good news for us. It keeps our lightning risk a little bit lower than what we would normally see on a typical afternoon in the summer for Florida. So anyway, we'll move on to the primary launch window forecast. And with that, you can see I have a 60% go for the launch window when it opens up in the early afternoon on Saturday. Winds pretty steady out of the east at 8 to 12 knots, which if you want to convert to miles per hour, that is 9 to 13 miles per hour. I know there's some weather nerds out there that might pick up on that. But anyway, temperature pretty warm, as you can expect. It is Florida, 86 degrees. Our main concerns for the primary launch window will be the cumulus cloud rule and the surface electric field rule. So then we'll go ahead and skip ahead to the backup window, which is actually Monday, and that actually improves. The weather improves a little bit to 70%, and that's mainly due to the fact that the launch window is a little bit later into the afternoon time frames, and with that we would expect the East Coast sea breeze to be positioned farther across the interior portion of the state, giving us a lot of sinking air behind it in general. So basically the weather looks good. I wouldn't be shocked if there are periods where we are technically red for weather, but the bottom line is that I don't expect weather to be a showstopper for either launch window. So with that, I'll go ahead and pass it back.
Okay, thanks very much. We will take some questions now. We'll take some questions in the room and on the phone line. A reminder to reporters to please limit to one question, and if you will state your name, affiliation, and who you're addressing your question, that would be a big help. So we'll start with Marcia Dunn.
Marcia Dunn, Associated Press for either of the Johns. It sounds like a bad sensor then. Is that your best hunch? And could it be anything else besides a bad sensor for the Monday's situation? And what would happen to an engine if the fuel wasn't cold enough at ignition? Would it just crack? Would it burst? Something else? Okay.
Yeah, I can start and then I'll let Dr. Blevins add in. Yes, we do think we know we had a bad sensor. That was our challenge early in the week, where we could not make the physics of the system line up to what we were seeing with that one sensor. So since then, we've had time to go back and look at the data and compare many sources of data and do some independent analysis that confirmed it's a bad sensor and we're getting good quality propellant through the engine. And so your question on the engine is there's a lot of things that we do on the engine to monitor the engine to make sure that it's operating the way we want to see it through operational flight instrumentation, as well as we have what we call an advanced health monitoring system that is on each engine that is designed primarily to look at vibrations and that sort of thing on the engine and pick those up as an early warning. And so, John, I'll let you add more there.
Yeah, let me follow up. The problem in part with the sensor is during ranges of temperature, it gave us the right slopes. It seemed to work fine, and then it did not give us an indication that we expected at the very cold temperature. So it really was an interesting signal, and that's part of the pause. It didn't just fail off scale or anything. So, but John is right. It is conclusive that that sensor was not a witness for what we were looking for. It's absolutely true. On the engine side, we do have advanced health monitoring. The reason we chill the engines for numerous reasons, but the primary one is for the high-pressure turbopump bearing. And that high-pressure turbopump bearing doesn't have to be all the way as cold as the liquid, but it's got to be cold. And if we know the liquid is going through, then we know it's about that temperature, and that gives us margin to that problem. And if it starts up and it's not cold, then it can skid. Ultimately, that causes excess wear on startup. That would manifest potentially as a shutdown during flight. It would be a red line. It wouldn't be, I'm not sure how you characterized it, but it wouldn't be an uncontained failure generally for that particular issue. I mean, but as John said, we have advanced health monitoring on the engines for a reason. These are high performance, really the highest horsepower per mass device that has ever been built. And so we need that health monitoring, and there's numerous things that we're looking for when we do that. So, but the sensor was bad, and in this case, what we're protecting against is a bearing skidding on startup and causing excessive wear.
Bill Harwood.
Yeah, hi, Bill Harwood, CBS. One question, Rachel, but it's got 2 or 3 parts, so sorry about that. No, it's pretty straightforward. What gets masked? I'm assuming you have to mask out the suspect's sensor, but where in the software do you tell it this is okay to start an engine, this is not okay to start the engine, and where would that occur? Is that before terminal count, or would it be at ALS transition? How does that work? And what, I guess another way of asking that question is, what tells the computers that the engines are at the right temperature to start? I mean, how is it knowing it's at that 420 degrees John mentioned yesterday to be able to press ahead with start?
I'll go ahead and take this one. So first of all, the protection for the engine is not, this sensor was never intended to be used as an LCC or for this purpose. It is not part of ALS. It is not part of the startup protection. Ultimately, the reason we use this sensor is to get an initial indication of cold fluid. We did combine this launch attempt 1 with an objective we did not achieve in wet dress, and that's why we had more verification work to do. We were going to do that verification early in launch attempt 1. This sensor failure prevented that verification, and that's why we had to go to subsequent measurements. And we were able to achieve that really only because we were in these conditions for a long time with fully tanked and flow through the engines. If we wouldn't have done that, we wouldn't be able to verify all that we could to verify that was liquid and that was a bad sensor. But ultimately, the protection for the engine that's in ALS are temperatures and pressures, but they're not the ones that we use for a long chill of the engine. If you reflect on the last answer, it was that, we're trying to chill the engine to get a bearing cold that we don't measure. And so that's buried inside of part of the engine. And so we count on a certain amount of mass flow for a certain amount of time in order to ensure that that bearing is cold. We did that during shuttle. We've done that during the entire program that used formerly the Space Shuttle main engines and now the RS-25s. And so that verification is a process verification we just didn't achieve in WDR4. That's why we were using this measurement. It's not part of ALS, so there's no masking in the computer software. All the normal protections are in place. We added an LCC. I asked Charlie to add an LCC for this verification because we just didn't receive it in WDR4. That's ultimately what this measurement is. It was never really intended for the purpose we ended up using it for.
So temps during chill down wouldn't play into whether or not to start an engine?
No, there are other temperatures that verify the liquid at the interface to the turbo pumps that were ready to go and other skin temps. This one was used as a witness for the bearing chilling for a certain amount of time and is not strictly relevant to the startup conditions.
Yeah, and John mentioned something that I want to pile on a little bit on. It's he talked about what we learned in the shuttle, and we did this engine conditioning through process control. And so I think I'd gotten a question about the difference between shuttle and SLS earlier in the week, and we had those recirculation pumps on the shuttle where we took that we took the heat out of the engine by circulating the hydrogen through the engine and carrying it back into the hydrogen tank to boil off, and so we're in the same situation here where we want to use our process control to assure ourselves that we're delivering the propellant quality that we need to the engines. And so, we had that process control on shuttle for these engines. It worked fine. We validated that process control when we were at Stennis for the green run, and our plan was on Monday to validate that for this vehicle with the configuration that we have on the launch pad. I talked to you relative to the differences between Stennis early in the week and the launch and what we have out at the launch pad. All those are still in the direction of goodness. We've got a bigger vent line on the ground side. It's insulated, which means we could flow more through that line. And our bleed system and our relief system is bigger than we had at Stennis. So all that still holds true.
Okay, we'll do stick with the front row here with Stephen.
Stephen Young with Spaceflight Now for Charlie. We're so used to seeing views inside the LCC, and on Monday we saw nothing, and your team was working so hard, and there's so much interest in this mission. I'm wondering, why are we not seeing any video in our isolated feeds or on NASA TV from inside the firing room?
Yeah, there will be views from the firing room that will be mixed in with all of the coverage.
Okay, Marcia Smith.
Online.com. I'm curious what the other limiting factors are and how many times you can attempt to launch. You have the flight termination system battery that you have to come back to the VAB to swap that out. Are there other limiting factors? How many times can you tank and detank? How many times can you give this a shot?
Yeah, I'll take a first crack at that one. Physics is one of the key limiting factors associated with the Earth and the Moon position relative to what this initial configuration of the Space Launch System rocket is capable of with the interim cryo propulsion stage. So we lose our ability to fly into a lunar intercept after September the 6th. And that's one of the key limiters. There's also the flight termination system. It's essentially a reliability check in the interest of public safety. And I don't know, Charlie, if you have any others to add on that, but those are kind of the key drivers at this point.
So you can tank and detank an infinite number of times?
Not infinitely. We track those, and we're a ways away from those limits.
Okay, Stephen, and then we'll go to Irene.
Stephen Clark, Spaceflight Now. Just so I understand, on WDR4 back on the 20th of June, ALS cut the countdown at 29 seconds for when it realized the engines were not thermally conditioned for flight. If the engines are not at the proper temperature on Monday, the sensor notwithstanding, ALS would still cut the count. There's no risk of igniting an engine at the wrong temperature. Is that a proper understanding?
Yeah, that's correct. I want to make sure you understand. ALS is checking the temperature, pressure, and many other parameters at that moment. The whole point of the sensor that we use, which we would have just verified process, as John talked about, is to get time at temperature for that one part, and now we've confirmed that through other means. So the engine will not start unless we hit the engine start box. ALS will shut it down.
And are you actually masking that?
No,
sensor?
we are not masking anything in ALS. No, we're not masking what we're measuring. That sensor is an engineering sensor for engineering data. It is not a flight. It's not OFI. It's not a flight instrument.
Okay, and we'll go to the second row to Irene Klotz, and then we'll take a few from the phone.
Thanks. Irene Klotz with Aviation Week, maybe for whomever. Do you think that starting the kickstart procedure early will give you a reading that the sensor is now working, even though it's just an engineering sensor? And do you think that just because they're engineering sensors and not the fidelity that you have elsewhere in the system and in the ALS software, that that's why the other engines were not quite cold enough either?
Yeah, let me take that. No matter what that sensor does, I've learned a lot about the flow process, which is what you do a WDR for, and we ended up unfortunately doing that somewhat on Monday. And we stayed at condition for a while, and we flowed not just through all four engines, but even through just the one that we were slightly more concerned about. And so whatever that sensor does, I have lots of supporting evidence that's much higher fidelity from the engine itself on that chill process. Starting it earlier certainly makes me happy because I'll get an indication earlier in the day that the engine's looking good. And time at temperature, as I told you, is what achieves a good bearing temperature, so we'll do that. As far as the other three temperatures, they're extremely consistent with saturated liquid temperatures. And, I think a lot of people have talked about those temperatures being off. In the case of Stennis, we had those three temperatures, and we defined what saturation was by what we measured at Stennis because we knew we had saturated liquid in the core stage green run. And in this case, if you're able to go back and take a look at that data, you'll see that they were at saturation temperature. So they may have been 1 to 2 degrees Rankine away from what we expected or what we saw as a witness prior 18 months earlier at the core stage green run. But they are consistent with saturated liquid, so there's no question that the engines receive saturated liquid. And quite honestly, normally, you would have done a WDR and you would have a few weeks to review that data, and there wouldn't have been that comment about it not reading on all these sensors and that kind of thing. We would have used all the evidence, and we've compressed that time, and we've got very good evidence, as John has said, that there's no question that we had liquid flow through that engine. And now we have other witnesses, and we'll use the data we have available when we do the kickstart procedure, and we've got lots of data in order to confirm that we start that liquid flow process.
Thanks. Okay, and we'll go to the phone and take a few questions from there. We'll start with Michael Sheets of CNBC.
Hi, everybody. I believe my question is for Mike Sarafin, but it's most specific to the amount of risk analysis you're looking at for a Saturday launch attempt. Based on the data that you've seen so far, given that this is supposed to be a full demonstration of the system, if there were astronauts flying on board this mission, would you still be launching based on the parameters that you're looking at, or are the risk analysis that you're considering different than if you were, launching the Artemis 2 mission?
Yeah, Michael, that's not an easy question to answer because again, Artemis 1 is the first test flight in a series of increasingly complex missions, and the next mission is intentionally Artemis 2 is intentionally our crewed flight test. So Artemis 1, we are buying down the risk associated with crewed flight on the next mission, specifically reentry of the vehicle at lunar reentry conditions. In order to get there, we have to set up those initial conditions using the performance of the rocket by getting it to the lunar reentry conditions. The rocket has to deliver us to the point of translunar injection. We want to shake down the spacecraft through flying out through the Van Allen radiation belts, the orbital debris field, and operate it in the deep space environment. Those are all things that we have to do with crew on board on the very next mission. And we know that there's risk involved with this first mission, but in terms of the incremental risks that we dispositioned today at the mission management team, it was a marginal increase in risk, and we are clearly ready to fly on Saturday with an understanding of what that risk is. We would have a very similar discussion on Artemis 2 if we had any of the conditions that we're seeing on this flight, and we would make an appropriate decision. So it's a hard question to answer because it presumes that we are successful on Artemis 1, and there's a non-zero chance that we will find something on Artemis 1 that will cause us to reassess our risk posture on a crewed flight.
We'll stick with questions on the phone, and we'll take our next question from Lauren Grush with Bloomberg.
Hi, thank you for taking my question. So, correct me if I'm wrong, but it sounds like the sensor that caused all the drama is separate from the critical sensors and other data inputs the engine computers use to know that they're in the right launch configuration. So why do you need that sensor at all? And was there an option during the countdown to cross-check against those engine sensors and inputs, or are you saying that there wasn't enough time to do that? Thanks.
Yeah, that's a good question. We do not need this sensor for flight. The sensor was set up to be engineering information for a chill-down confirmation process. And what we're trying to do is make sure that we have cold liquid for a certain amount of time, just like we did on shuttle, to infer that the rest of the hardware is cold. And that's what we're trying to do, is just chill that down. That's why we call it the chill process. This sensor is not used for that time. Those sensors were deadheaded that you would use at that particular time and were not appropriate references for us. In fact, that's not what we're using to confirm that we had liquid flow through the engine per se. And so, that it was an engineering analysis where we combined the wet dress with the launch attempt, and we were unable to confirm that chill process, and that's what stopped us.
Yeah, and John, let me add a point here. We had a plan going into the August 29th launch attempt, and it used these sensors to help confirm the proper thermal conditioning of the engines. We had trained that plan, and then we ran into other issues. We ran into a leak at the tail service mast umbilical, and then we had a vent valve that was not operating properly. So we were off the script in terms of the normal tanking operation, and the team did a fantastic job working through the managing of a hazardous condition. And one of the worst things that you can do when you find yourself in a hazardous condition is just go even further off script and to deviate and get into an operation that you're not prepared or trained for. So the team did absolutely the right thing on the 29th, and they knocked off the operation, and they knocked off the test, and they got us into a safe configuration, and then they spent the last couple of days reviewing the data, and that was absolutely the right thing to go do. 2020 hindsight, these particular sensors we know aren't the best cue to work off of, and we've reassessed the plan, and we have a great plan moving forward. We understand the risk posture associated with getting the engines thermally conditioned, and the team was asked today very specifically, are you ready to go load the vehicle with this earlier tanking and earlier bleed flow operation? And the answer was absolutely yes. So I don't know, Charlie, if you have anything to add to that one.
No, I think you covered it.
Okay. Our next question is from Eric Berger with Ars Technica.
Hi, thanks for doing this. That was great, Mike. Thank you. I'd like to take another crack at a question I think Marcia was trying to ask earlier. Based upon comments we've heard during earlier briefings, it does seem like there's been some mild concern about the shelf life of the stacked Artemis 1 rocket. And I guess what I'd like to understand is, are there wear and tear issues that you've mentioned on the rocket? Marcia asked how many cycles were left in the core stage propellant tanks, and just wondering, are you feeling some urgency to get this rocket off in the next month or two, or are you good in the configuration you're in now for quite a while? Thank you.
We're good in the configuration we're in for a while. As I alluded to earlier, I'm not going to give you an exact number, but I know we're well into the high double digits on additional tank cycles. As far as worrying about things with the rocket sitting on the pad, there are probably more little things like we see cracks in TPS and that sort of thing that we have to go analyze to clear. But the big thing we want to avoid is rollbacks to the VAB. Those are the things that Dr. Blevins has told me will put more stress on the vehicle than anything else. Now, that said, we've still got rolls left in the vehicle, but we want to watch that and manage it. Do you want to add anything, John?
I'll say we track all life-limited items. We watch that very closely. I don't have any concern on the pressure cycles of the tank, just as you said, John. We have numerous cycles left, and that's to a good margin of safety. I do like to protect the rolls because they're complicated, and they affect every part of the rocket, but we have plenty of rolls left at this time, too.
Okay, one more on the phone, and then we'll come back in the room. Joey Roulette with Reuters.
Hey, thanks. My question was asked.
Okay, we'll come back in here in the room. We'll go there in the second row, Jeff Faust.
Jeff Faust, Space News. For Mike Sarafin, quick question. If we do launch on Saturday, what is the length of the mission? And do you have to do any changes to the mission plan if it's shorter than 42 days?
Yeah, Jeff, that's a great question. I will confirm it here, but I believe it's a 37-day mission with the splashdown on October the 11th. In terms of changes to work, obviously you launch a day later. You have to schedule your satellite coverage and your deep space network coverage. You have to issue a whole host of notifications, and some of those are to aircraft that are going to be taking observations of the vehicle during launch or during splashdown. We've notified the Navy that's providing our recovery assets. We've notified the FAA via the Eastern Range for notice to air missions. We've notified the Coast Guard for notice to mariners for any boats that are out there, for the splashdown locations of any of the jettisoned items, but also of the end of mission locations. So there's a whole host of things that the team works through to replan, and all of those notifications, but also products have been pre-planned ahead of the mission, and the team has pulled those off the shelf. They're putting the final touches on a lot of those things, and the process is flexible enough to handle that. So we're not concerned with any of those items.
Okay, we'll come back here in the front row, and then we'll move over to the other side. Right here, yep.
Chris Gephardt with NASA Spaceflight. I think these are both for Charlie. How many cutouts and colas do we have for Saturday's window? What's the longest one within there? And starting LH2 chill down on the ground side a bit early, starting to bleed a bit early, that sounds to me like you're going to lose a little bit more to boil off and a little bit more to bleed. Where does that leave you on the LH2 margins for the day? I know you have to top off the tank afterward, but like on launch day, where does that leave you for the 2-hour window?
Let's see. I'll start with the colas and cutouts. So I probably have a report that's in my email. We get those at L-2 day. So I haven't looked at it specific to our next opportunity, but I can tell you that for our previous opportunity, we had somewhere in the neighborhood of about 30 to 40 cutouts, so it's a fairly significant number. Most of them are really short, just a couple of seconds long. We did have a couple that were a little bit longer, maybe on the order of a minute or so. But I can absolutely get you a specific number. And then, let's see, what was the second part?
Starting the chill down in the bleed, yeah.
Starting it earlier. So we went off and analyzed that. You're absolutely correct. If you start it earlier and you start the bleed earlier, you're going to consume more. And we did go off and look at that, did the analysis. We will be able to support the entirety of the window, but we will have a little less margin in the tank when we're done.
Okay, thank you. We'll go here next.
This question is for Mike Sarafin. My name is Ada Monzon, Guapa TV, Puerto Rico. Can you elaborate on the plan of next launch windows? Even if it's not next Monday, then what are the choices or the opportunities even by the end of the month or by October?
Yeah, it's a great question. And for Jeff, I did verify that October 11th is our splashdown date, and it's a 37-day mission. So in terms of mission availability, we do have a reservation with the range for September 5th. So if we do not launch on Saturday, we'll be looking at a afternoon launch on the 5th. The 6th is in play. It's a fairly short launch window on the 6th of September. Should we not tank on the 5th, we may elect to move to the 6th. Once we get past the 6th of September, September the 19th is the earliest from a physics-based standpoint that we could pick it up. And then that launch period ends on October the 4th. Obviously, we would need to account for when did we roll back to the vehicle assembly building and what that looks like relative to where could we pick it up. We would also have to assess why did we roll back to the vehicle assembly building? Did we just simply not get lucky with weather and we had to roll back and check out the flight termination system again? Or was it a technical issue that requires access to a very specific part of the rocket? We would have to look at how long does it take to gain access, the availability of spare parts, or any reason that we would have rolled back. So there's a whole host of variables in there, but that gives you a sense of kind of the relative time frame.
Okay, let's come to the other side of the room here. We'll go to Ken Kramer.
Hi, thank you. Ken Kramer, Space Up Close. For Charlie Blackwell-Thompson, please, can you talk a little bit more about the liquid hydrogen work you did on the purge can? How did you discover it? What did you do to fix it, and how do you determine it was fixed? Thank you.
So, after WDR3, we also had a leak in the purge can, and while you never want to have a leak, it did give us an opportunity to really do a very close examination of what caused that leak. And so we learned a lot from that, and we learned what are all the things that you want to go check. And we took some very specific actions after WDR3. You may recall we were setting up very similar to what we did over the last day or so out at the pad. We were getting the access in place, and then we made a decision to roll back because we wanted to go allow the GN2 production plant to make the upgrades. And so we went back to the VAB and opened up the purge can. We looked at all of the penetrations that go into that can, the soft goods associated with it, looked at the gaskets, looked at the flanges, checked all the torques, and found that there was some relaxation in the torques on the flange, and we ended up retorquing them. We made a couple of changes to the drain assist purge. You may remember seeing the pictures. It was kind of a cantilevered, arrangement into the back of the can, so it kind of put a load on there. We ended up changing that, and anyway, we came back out for WDR4. We saw good performance. In the purge can, we obviously picked up the 4-inch QD leak, so that presented a different challenge for the team to go take on. But what we saw during launch attempt 1 is we saw a similar signature. We had hydrogen concentration increasing. It was fine during slow fill. It was as we got into the higher pressures and saw more flow across that interface. We were able to manage our way through it. The team was able to vary the flow rates and stay within the specifications. But certainly we saw it reoccur during drain and recognized that we needed to go take a closer look at what was causing this. So as I said, we went back into the purge can out at the pad because we'd had the opportunity after WDR3 to come up with, here's the 3 or 4 or 5 things you need to go look at. We went and checked all those same things again, and what we found is in that 8-inch in the purge can and in the 8-inch QD, there is a pressure sense line there. It's a penetration into the can and into the 8-inch there. And what happened is we found that loose, and we believe, we found that loose. So we changed out the seal around that pressure sense line. We retorqued it, and we believe that that is most likely the leak source. We checked the flange. The torques on the flange, everything was nominal. We did an inspection of the gasket. It was nominal, and we checked every other fitting there, and everything was found to be nominal. So finding that one item loose, we feel that that's most likely the cause. Now, as we've talked before, we did ambient leak checks, and afterwards, after we put it all back together, and we didn't find anything, but until you hit it with cryo, you really don't know for sure. So. No, I mean, I have to believe that it was something that's happened between when it was checked in the VAB and at the pad. So it could be from roll or from something else, but no, I don't know for certain what caused it to become loose.
Okay, we'll take here in the black shirt.
Hi, Michael Grushko, National Geographic. This is from Mike Sarafin. Following up on Michael Sheets' question earlier. Earlier in the week, you gave an assessment that there was a 1 in 125 risk of loss of Orion based on all phases of flight. Now you've added 2 incremental risk acceptances to the mix, the foam and then the engine conditioning. Do you have an updated number, and if so, what is it?
We don't have an updated number. What I would say is there was no appreciable increase in risk. There was a delta risk acceptance because we know we have a crack in the foam. We have a nonconformance at the intertank flange area. We know its location. We know the approximate size, and there's a small likelihood that it could be liberated during launch, follow a very specific trajectory, and hit one specific location on a booster that could cause a problem. The likelihood of that is very low. In addition to that, as we talked with the engine bleed, the thermal conditioning, it really comes down to the fact that we haven't demonstrated it previously. We have a high confidence that we can get through this, given the indications that Dr. Blevins and John Honeycutt talked earlier. The team has more insight given where we are. We've trained it. We have a more robust plan than we had going into the launch attempt on the 29th. In terms of what that means to 1 in 125, does it change that number? Probably if you go way out in terms of decimal points, but there's no appreciable increase in risk. But we do talk about those types of things to ensure that we understand exactly what we're getting ourselves into before we commit the vehicle to flight.
And next we'll go with Kenneth Chang, and then we'll take a few more from the phone.
Hi, Ken Chang from New York Times for John Honeycutt, John Blevins. Could you explain in a little more detail what was the issue with the vent valve on Monday and how you're confident it's not an issue going forward? Thank you.
Yeah, so we did not have an issue with the vent valve. The vent valve is in the system where we had the leak. So the vent valve was inside of the inner tank. and it goes to the inner tank structure, and then there's an umbilical there that vents out to the ground, and so the team saw the leak there. So it's probably better for Charlie to answer that one.
Yeah, so I think John described it really well. So this is part of the hydrogen tank vent system. Goes out the umbilical arm, very similar to when we talk about the TSMU, right? There's a ground side and a flight side plate there, and the leak that we picked up was in that particular cavity. What we believe happened is as we have seen with QDs or quick disconnects before, is when you change the environment on them very rapidly, sometimes you will see a shift in the seal. That's actually one of our troubleshooting steps that we do when we see a leak. Is we'll let the QD warm up, and then we will allow flow back across it to see if we can get it to seat. So what had happened in the particular situation that we saw with that is we had gone all the way through our loading. Everything was fine. We had nominal performance in that QD cavity, no issues at all. But when we got into the troubleshooting of the bleed issue, that QD warmed up. We had not had, we'd had the vent valve closed, so you're not really venting through that area, and you got it warmed up for quite an amount of time. And then when we opened it and we exposed it to a very rapid change in environment, both temperature and pressure, that's when we picked up the leak there. And as a matter of course, as we went through the drain operations a little bit later, and you saw, the QD chill down, you actually saw nominal, the leak kind of sealed itself. So that's why we have confidence going into our next tanking operation. Again, we've seen this in the past where you've had rapid change in temperature and pressure. Sometimes you'll see some change in the seal, and that's what we believe caused the issue that we had on our launch temp 1.
Okay, we'll take a few from the phone. We'll go to Marina Corin with The Atlantic.
Hi, I'm Marina Corin with The Atlantic. A question for Mike Sarafin. A few days before the first launch attempt, you said that if you couldn't successfully demonstrate the thermal conditioning of the engines, you wouldn't be launching that day. Now that you're confident that you'll be able to do that on Saturday, what else is on the table, something of a similar nature that you haven't tested yet that you can say today could be another showstopper?
That's a good question, Marina. Certainly, we have nearly 500 launch commit criteria, and 489 launch commit criteria. Any one of which affects our overall risk posture headed into the launch attempt. So this was one particular situation that coming out the engine thermal conditioning was one particular and very unique situation that we carried out of the agency flight readiness review as a known first-time demonstration in the launch countdown. Unlike the other launch commit criteria, we just knew that this was something that we had to do successfully for the first time. The other launch commit criteria, obviously we've got to meet those or we get into elevated risk acceptance, and we do reserve the right to do that, but it would have to have adequate flight rationale. So, things like weather and a whole host of other criteria are part of our launch commit. So we will wait and see what the conditions are, and we will go when the vehicle is ready and we understand the risk posture.
Okay, we'll take another from the phone. We'll go to Ramin Skiba with Wired.
Hi, thank you. My question was answered, but I'll ask something else. I guess this is for Mike Sarafin. I was just curious, will the Vice President or any Congress members or celebrity guests be in attendance on Saturday?
Obviously, Artemis 1 in this initial launch of the Space Launch System rocket and the Orion spacecraft around the moon is gathering and garnering a lot of attention nationally and internationally. We will have VIPs here. I don't have specifics on who the VIPs will be, but I would be surprised if there were not congressional stakeholders here.
Okay, and we'll come back to the room here. We'll go here in the hat.
Kristen Fisher with CNN. I've got one more question about the bad sensors, so I think this is for one of the Johns. But I just want to try to simplify it a little bit. Given that you have confirmed that this is a bad sensor now, is part of the plan, is part of the risk posture for this second launch attempt to simply ignore it?
Yeah, let me answer that. It's not a risk posture per se, because what we always wanted to do is confirm that we could get liquid in for a certain amount of time to chill the engine, and now we've confirmed that. So we weren't going to use this instrument for that purpose once we confirmed it, and now we've confirmed it. So I don't know, to me, if I would call that an increased risk posture going into launch. I think the risk that remains is that we haven't gotten to our first launch of the program yet. What's the risk in ignoring that sensor?
Is part of the plan, is one of the things that you all could do on launch day is just to ignore the sensor, the bad sensor. Would you just ignore it?
Yes, we will.
Okay. Thank you.
Yeah.
Okay, we'll go in the next row back.
Manuel Masanti from Debate. So if you can ignore that sensor, can you ignore the other three? So you have one sensor per engine, right?
Yeah, there are three more sensors.
So can you ignore the four of them?
We use those to make sure the initial flow looks cold, and we're going to try to take a look at that. We have other witnesses, and we know those witnesses well now that we've done this test. And so, I won't say that we're ignoring them, but I will say that we have witnesses. What Charlie's doing for the engines is early in the count, and we will have sufficient time to verify we've got good liquid in the engines, regardless of what any of those sensors do.
Okay, we'll go back and take a couple from the phone. Next up is David Curley with the Discovery Channel.
Thanks very much. Honeycutt or Charlie, what are your tolerances? What is the margin? I asked this a couple of days ago. When hydrogen's coming out into the vent tube, what temperature should it be at? If you're trying to get to minus 420, what it should be at? And Sarafin, big picture, we're in the weeds here. We're Thursday after a scrub going into the next launch. What are you thinking? How are you feeling?
Temperature.
Yeah, what we're looking for roughly is, we're looking for saturation temperature, and that's a function of pressure, and it's around minus 420 F, as you mentioned. I'm not sure what you're asking about. There is margin between that. There's roughly 40 degrees Fahrenheit margin between what we need the bearing to be and what we're looking for the liquid to be. And with the time that we're using, we will have plenty of cold fluid through there. So, ultimately, this process really ensures there's virtually no risk that that bearing isn't at the right temperature. So I don't know how to measure that in any kind of quantitative margin. I would just suggest we verify that we can chill the engines properly.
Okay, and David, in terms of what am I thinking, what am I feeling, we got to show up, we got to be ready, and we got to see what the day brings. And, we've got a whole host of things that could cause us to not get off any given day, weather, range, or technical. And those are the three big buckets. We talked about the 489 launch commit criteria. Those are the technical reasons we might not launch that day. And we've got the weather forecast is favorable. We might find that a combination of technical issues or somebody being out there on the range that shouldn't be out there from a public safety standpoint, and just a cloud cell or that kind of stuff could cause us to miss the opportunity. There's no guarantee that we're going to get off on the 3rd, but we're going to show up and we're going to try and we're going to give it our best.
We'll take another question from the phone and then come back to the room. Next up, we have Tim Fernholz with Quartz.
Hi there, this is Tim Fernholz from Quartz. Thanks for taking my question. I hope we get a launch on Saturday, but I'm curious, can you tell us a little bit more about the eclipse violation? I know obviously that wasn't one of the days that was originally hoped for a launch. What are the risks associated with that later on in the flight, and why are you accepting them now? Thanks.
Yeah, Tim, I'll say that the finding or the analysis that was brought forward at today's mission management team meeting was some relatively late analysis. Normally, the team prioritizes the normal mission plan first, the mission you intend to fly, and they go off and they analyze that, and they did that work. And then they start looking at all the what-if cases. What if we have a performance problem? What if we have a battery problem? What if we have a solar array problem? And this was one of those what-if cases, and it came back and it showed that we had a significant power deficit if we had a performance problem, and we expect the rocket to perform fine. We've looked at our performance margins. We have over 20,000 pounds of margin to our guided cutoff at the insertion altitude, and we have over 2,000 pounds of margin to the point of translunar injection. But the power deficit, should we have a performance problem through the point of translunar injection, was to the point where we did not think we could manage it on the Orion spacecraft side, just due to the geometry between the sun, the Earth, and the spacecraft as it was headed outbound towards the moon on that outbound leg. So we took it off the plate. That said, it's likely to be a moot point once we tank on the third. The fourth is off the plate anyway, simply from a commodity standpoint. So it was just a part of our look ahead, and it was, as I said earlier, the result of a what-if case that came in fairly late.
Okay, and we'll take one final question here in the room, and then we'll go ahead and wrap up. We'll go in the second row here.
Hi, Sophie Sanchez from Cosmic Chicago with Chicago Now. I think my question would be best posed to Charlie. Tuesday's briefing kind of brought up memories of the ICE team and the work they did during the final inspections of the pad, looking at things like abnormal engine temperatures and foam falling off due to cracks. What role do they have, if any, in final inspections of SLS? And did they provide you with any information or data during the countdown, or was it all coming back from the sensors, the data gathered? Thank you.
So the ICE team is a really important part of my launch team, just like they were back in the space shuttle. And one of the things that they do today, just like they did back then, is they provide an L-1 hour report on all of their findings. One of the differences is that they utilize high-res cameras out at the pad, and we've specifically placed additional cameras so that they have multiple views, and they can look at that without having to be deployed to the pad. So we've allowed technology to assist them in doing their job, but the report, in terms of the kinds of things that they're looking for, the report that they make is very similar to what they did with shuttle. It's just that they're doing it remotely. And we also have the capability, should we ever need to, if we had something where we felt like we needed to send them to the pad, we certainly have the capability to do that. We could send them in as a red crew to go evaluate something very specific. But what we have found is that the imagery that we get back in the control center has been more than adequate to evaluate all the different areas and the performance of the core stage.
Okay, thank you. With that, I'd like to thank everyone for joining us today. We will have another pre-launch status briefing tomorrow morning at 9 a.m. Eastern, and our coverage of tanking operations starts on NASA TV Saturday at 5:45 a.m. Eastern, with our full launch coverage starting at 12:15 p.m., and our Spanish language coverage starts at 1 p.m. You can find more on our coverage plans and on the mission at nasa.gov/Artemis.